Welcome to This Explainer. Today, we are stepping right into the fascinating, completely hidden world of modern structural engineering. We're going to peel back the layers, literally, on a brilliant design secret that is quietly holding up the world around you, from the floors you walk on every single day to the actual spacecraft orbiting our planet right now.
So it all starts with a universal engineering challenge, right? How exactly do you build structures that are incredibly stiff and strong, but weigh almost absolutely nothing? Normally, if you want to add strength, you have to add mass. But in fields like aerospace, transportation, or advanced construction, heavy materials are a massive, massive penalty. You essentially need materials that are 90% empty space, but can still stop a bullet or hold up an entire bridge. You need the ultimate perfect balance of high strength and low density.
Section 1, Intro to Sandwich Composites. The elegant, frankly brilliant solution to this exact challenge is something engineers call the sandwich composite. It is a total masterclass in using material geometry to just completely cheat the traditional rules of weight and strength. And the anatomy is deceptively simple. It consists of two incredibly thin, stiff outer skins separated by a thicker, exceptionally light core in the middle. When they are bonded together into a final panel, they become an absolute structural powerhouse.
The absolutely crucial point here is the mechanical balance between these layers. The skins are made of materials with a high modulus of elasticity, which is just a fancy way of saying they are very stiff and strongly resist being stretched or compressed. The core, on the other hand, is much thicker and needs a really high shear modulus. Its main job is to support those super thin skins so they don't buckle or deform under pressure, keeping them perfectly fixed relative to each other. This delicate balance ensures that neither material fails prematurely.
Section 2, the physics of strength. To really visualize how the mechanics work under pressure, just think of a classic I-beam. A sandwich panel is essentially an infinite I-beam. The composite skins take on the exact same role as the flanges, doing all the heavy lifting, while the core acts as a continuous, totally spread out web supporting them across the entire surface area. When external bending forces are applied to this panel, the skins and the core immediately take on different jobs. The top skin might be subjected to intense compression, squeezing together, while the bottom skin is handling extreme tension, pulling apart. Together, they form a resisting moment. Meanwhile, the core is working incredibly hard in the middle to resist shear stress, basically stopping those skins from just sliding past one another. To really grasp what shear stress is, imagine bending an unglued deck of cards, or maybe a really thick telephone book. Because the core here is weak in shear, the individual layers simply slide or shear past each other. The outer layers experience very little stress because the core just deforms super easily. It has a low shear modulus. But look at the dramatic contrast when you adhesively bond all those layers together. Boom! The deck is no longer free to slide. It becomes incredibly stiff. By forcing the core to resist that shearing action, the panel can now only bend if the top layers physically squeeze together and the bottom layers physically stretch apart. Having that high shear modulus is literally the secret to the composite's massive flexural rigidity.
Section 3, Exploring Core Materials.
Okay, so stepping out of the realm of theoretical physics and into the physical materials engineers actually use in the factory, there is a huge variety of materials used to build these ingenious cores, but they generally fall into three main buckets: natural wood, high-tech honeycomb structures, and synthetic foams. Let's look at how each one brings something totally unique to the table.
Long before engineers were designing aerospace panels, nature had already perfected the sandwich core with wood. Wood is an unbelievable natural composite. Its longitudinal strength actually comes from crystalline cellulose microfibrils, which are basically linear polymers bonded covalently and by hydrogen bonds. It's the original, naturally occurring structural composite.
Now, for modern, crazy, high-performance applications, we usually turn to the honeycomb core, often made from things like aluminum, fiberglass, or aramid. The honeycomb geometry optimizes force transfer perfectly. If one cell wall happens to break, the surrounding arms just easily carry the load. It provides the absolute highest shear stiffness to weight ratio available, which makes it totally essential for commercial space vehicles and advanced automotive designs like the ultra-lightweight Hyundai Karmaka concept. And it does this mostly because that honeycomb structure is overwhelmingly just empty air doing incredible amounts of work.
Section 4, Manufacturing Sandwich Panels.
So how do we actually build these advanced materials? Well, creating a honeycomb core often involves this brilliant corrugation process. Raw material sheets, like giant rolls of aluminum, are fed through gear presses to create corrugated sheets. These are then carefully stacked, bonded, or welded together at the nodes, and then actually pulled and expanded. This expansion produces a very low-density cellular block that can be sliced to the exact, precise thickness needed for the core.
Now, sometimes honeycomb is replaced by synthetic foam, usually to reduce costs or to drastically improve fire resistance. This requires a really cool three-step foaming process using a blowing agent. First, heat causes the blowing agent to decompose and release gas. Second is nucleation, where a sudden, rapid pressure drop creates tiny little sites for bubbles to form. And finally, cell growth happens as the gas diffuses into these bubbles, expanding the entire material into a lightweight foam.
What's truly fascinating here is how carefully engineers have to control the heat and pressure over time. Whether they are dealing with homogeneous or heterogeneous nucleation, dictating exactly when and how those tiny bubbles grow ensures a totally uniform cellular structure. And that is absolutely vital if you want consistent structural strength across the whole panel. All right, so once we have our core and our outer skins, we have to bond them together permanently. For flat boards or simple preformed panels, engineers generally use a heated press, applying direct, heavy temperature and pressure. But if the design requires sweeping, complex curves, they rely on a highly versatile method called vacuum bagging.
To build a finished product using vacuum bagging, the core, the pre-impregnated skins, and the adhesives are all carefully assembled on a mold. Then, a vacuum bag is sealed over the entire shebang, and a pump literally sucks all the air out. The sheer atmospheric force of the vacuum presses all the layers perfectly together against the mold, consolidating them tightly while they cure into a single, incredibly rigid, incredibly lightweight panel.
So from the floorboards of the airplanes we fly in to the walls of modern high-speed trains, this simple but profound ABC architecture is quite literally everywhere. The next time you encounter a structure that seems impossibly light, yet incredibly rigid, you'll know the engineering secret hidden inside. So I want to leave you with this. Take a look around you today. Where else is this hidden sandwich geometry secretly holding your world together? Keep your eyes open and keep questioning how the world is built.